Okay. I apologize that the meeting did not work today. I'll see if I can figure out what's causing that. I'm not sure what the problem is. But I'm going to go ahead and record these notes that I was going to give to you, and I'll send these out so that you can watch them. So the question that we were thinking about is, do heavier objects fall faster? So we want to know, if we drop two things at the same time, is the heavier object going to fall faster? And so we're going to watch this video real quick, and hopefully it will show up fine. Didn't do so well in the meeting, but hopefully it'll work better.
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct.
This is NASA's Space Power Facility in Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out 30 tons of air. Galileo's experiment was simple. He took a heavy object and a light one, and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air.
Okay, we dropped 2 Militor in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop. 10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Look at that.
They came down exactly the same. Wow. Look. How they hit right there.
Exactly
Mom,
the same. Exactly the same.
Pictures on this phone,
Nothing. Look at that.
but I can't how to get on pictures.
Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this.
All right, and I'm going to go ahead and stop that there. He goes into sort of Einstein's theory of relativity, which is not really what we need to know about, because we were mainly thinking about Newton's laws here. But the reason that we sometimes think heavier objects should fall faster is many times heavier objects have less air resistance. So when you saw the feathers and the bowling ball dropped first, the feathers took a lot longer to hit the ground. But the feathers have a lot of surface area and a lot of air resistance, whereas the bowling ball does not have as much. But whenever you saw all of the air sucked out of that room, there, it's a giant room at NASA that they use. It's a vacuum where they suck all the air out, so it's just space. It would be similar to what it would be like if you were out in space. And you drop those two objects, there's no air resistance, so they fall and hit the ground at the same time. So whenever I asked earlier if you dropped a bowling ball and a basketball at the same time, which would hit first, in general, they should hit at about the same about the same time. They have similar surface areas, similar air resistance, and so even though the bowling ball is a lot heavier, it is not going to hit earlier. You could try this at your house. Just find two objects that one is heavier than the other, and try dropping them at the same time and see if that happens. Now, obviously, if you use something like a piece of paper or a feather, it's got a lot of air resistance, and it's going to take a while to hit. But for example, if you try to drop a paper clip and a softball at the same time, they're probably going to hit at about the same time. So try that at your house, see for yourself. The other question I want to ask is, do falling objects fall at a constant speed? So are they falling at the same speed the whole time that they're falling? So we're going to look at this other short YouTube video here. And hopefully it'll come up pretty quickly. And what you're going to see here, this is just a video of somebody dropping a ball. And I'm actually going to pause it here. And I'm going to slow down the speed a little bit on this one so that you can see it more closely. So let's play at this slow speed. Music's going to sound funny. But you can see every, here, like 10th of a second, they're pausing that ball. And what you should see is each time it's fell a little bit further. It's going to do it one more time. Could cut the sound off so that we don't hear it. It'd be strange. But you can see right here there's 2, 3, 4, 5, 6, 7, 8, 9. And you can see there's more space in between each one of these lines. It's a little further apart. That's because the ball is speeding up. So whenever we drop something, it is at rest. It's not moving at all. And then when we drop it, gravity causes it to accelerate. So if you drop a ball from 3 feet, it's not going to be going very fast whenever it hits the ground. But if you drop a ball from 100 feet, it's going to be going a lot faster whenever it hits the ground. So if somebody drops a softball from 3 feet onto their toe, it might hurt a little bit. But if you drop a softball from 100 feet onto your toe, it's going to hurt a lot more, or possibly cause some serious damage. So a very famous scientist you've probably heard of before, Galileo Galilei. Galileo is probably somebody you've heard of before. He was an astronomer. He found that objects accelerate as they fall. That means that they get faster and faster and faster. They do not fall at a constant velocity. So on Earth, if we ignore the effect of air resistance, objects fall according to the formula D equals 16t squared, where D is the distance fallen and T is the time in feet. Now, this only applies on Earth, because if we go to other planets or the moon or something like that, which we're probably not going to do, but if we did, those planets are going to have different amounts of gravity. So something on the moon is going to have a different formula than you'd have here on Earth. We also must ignore air resistance. So if we're dropping feathers, then this formula is not good to use. But if we're dropping a fairly dense, heavy, or fairly dense object, something that doesn't have a lot of air resistance, then this formula applies fairly well. Of course, if we were wanting to be very precise, we'd have to include air resistance, but that would make the formula way too difficult for us to do ourselves. So let's look at this scenario. let's pretend that we have an object and we're going to drop it from a height of 100 feet. And so we want to make a chart of the height of the object over time. And so at time 0, before we drop the object has not fallen at all, and it's 100 feet above the ground. So I'm going to pull up the calculator over here. Let's see if I can make this just a little bit smaller. Let me get rid of this. And let's pull up Desmos over here. And make this smaller also. Okay. And so the formula that Galileo told us was that the distance fallen is 16 t squared. So after 1 second, I would have 16 times 1 squared, and that is just 16. So after 1 second, the object that we've dropped has fallen 16 feet. So if I want to know its height above the ground, if it started at 100 and it has fallen 16 feet, I would just do 100 minus 16. And if I do 100 minus 16, I'll see that the height of the object after 1 second is 84 feet. Okay, so I'm going to continue. Galileo's formula tells us after 2 seconds, we're going to have 16 times 2 squared. That gives us 64 feet. So after 2 seconds, the object has fallen 64 feet. Now this would be 64 feet total, not 64 feet in addition to the 16 that's already fell. It's going to be 16 feet total. So if we take 100 and we subtract 64, we're going to get 36 here. And if we continue on with the table here, 16 times 3 squared is going to give us 144. Now here's our problem. Our formula quits working here because the formula tells us that the object will fall 144 feet in 3 seconds. But we were only 100 feet above the ground, so the object cannot fall 144 feet. So at this time, we're going to be at 0 because it wouldn't make sense to be at negative 44 feet. Okay, so this next part asks us to write an equation using height and time that gives the height of the object above the ground. So if we think about what we just did here, we're supposed to use height and time. We're not supposed to use distance at all. What we were doing is we were taking our height and we were doing 100 minus the distance that had fallen. But this asks us for height and time, not height and distance. But to find that distance, we use this formula, that's 16t squared. So I'm going to take that and put this here. So we could say that the height equals 100 minus 16t squared. And if I go over here, and if I make myself a table, if I say this is x1, I'm gonna call this h1. Oh, h1. And then I'm gonna call this, oh no, I'm sorry. Let's call this t1. So that's t1. And we're gonna say h1 equals 100 minus 16 T1. Okay, so let's see if this will work here. Let me drag this over a little bit. So if I plug in a number like 1, I get nothing. Okay, maybe I can't do it. Maybe I've got to do x's and y's. So I'm going to use a x1 like it had. I'm going to use a y1. Maybe I don't put that equals. Maybe I just do 100 minus x1. Okay, there we go. And you can see, let me plug in 0, 1, 2, 3. Oh, I didn't square this. That's why I'm not getting the right numbers. That's one too many. There we go. Okay, and now you can see we're getting the right numbers. Now notice here it does give us negative 44 right here because it's going strictly off the numbers and it doesn't know that we've already hit the ground. So this equation right here, our initial height is what we call this 100, minus this factor due to gravity gives us the height of the object. Well, this can be really useful in a lot of situations. So let's think about this. If we want to know how long it takes the object to hit the ground, well, whenever the object hits the ground, I can look over here at the table and I can tell that it's somewhere between 2 and 3 because I know the height is between 2 and 3 there. But whenever something hits the ground, that means that its height is 0. So I could take my formula, h equals 100 minus 16t squared. And I could put in a 0 right there for that h. And so if I want to solve this, I could subtract 100. So I get negative 100 equals negative 16t squared. I would next need to divide both sides by negative 16. And so I'm going to go over here and do negative 100 divided by negative 16. And that gives me 6.25. So I've got 6.25 equals my t squared. And the last thing I'm going to do is take that square root right here. And so if I do square root of 6.25, I'm going to get 2.5. So in 2.5 seconds, if we drop an object from 100 feet, it should hit the ground. Now that ignores air resistance, so it might actually take just a tiny bit longer, but it'll be somewhere around that. Now let's consider something. What if the object was dropped from 75 feet instead of 100 feet? How would the equation change? Well, let's just think first about what the equation looked like to begin with. So we had h equals 100 minus 16t squared. That was our equation. Well, in this case, if we're dropping the object from 75 feet instead of 100 feet, clearly what needs to change here is that 100. So this would be 75. Okay, so now if we want to know how long it would take for this object to hit the ground if it was dropped from 75 feet instead of 100 feet, then we could do the same thing we just did, but with our new equation. So our height would be 0 whenever the object hits the ground. So we'd do 0 equals 75 minus 16t squared. And to solve this, I'd have to subtract both sides by 75. So I'd get negative 75 equals negative 16t squared. And I could divide by negative 16 to get rid of that. So divide by negative 16. I'll do that over here using my calculator. Negative 75 divided by negative 16 is going to give me 4.6. So I've got 4.6875 equals t squared.
On there, change 1H.
All right, do 1H.
Hey, that's nice.
All right, Henry's going to draw you 1H. Okay, good job.
Thanks.
You're welcome. All right, so this equals t squared. And so last thing is we just need to square root both sides.
How do you get on the other pictures? How do you get on the other pictures?
Okay, so if we square root both sides, that means we're taking that square root of 4.6875, and we're going to get that big number, so I'm going to just round that off to 2.165. Technically here I would have a plus or minus when I solve that equation, but you don't need the minus. It would make sense that something hit the ground in the negative time in the past. If we only dropped this object from 75 feet, it would take 2.165 seconds to hit the ground. So that sort of gives you a little bit of an idea of how to set up these equations. Now let's look at a couple more things it could be used for. Let's look at this example. Aiden drops a pebble off a tall bridge. It takes the pebble 5.5 seconds to hit the ground below. How tall is the bridge? So in this case, we know we would have an equation. Our height would equal some number right here minus 16t squared. Now, I don't know what that number is. I'm going to call it this fancy term right here, h sub 0. Now, the reason I'm using that is because scientists use that a lot whenever they're talking about these problems. So, you can just think of that as another variable. That is our initial height. So, h sub 0 is the initial height. And initial height is just your beginning height. In this case, it's how tall the bridge is. It's what we're looking for. So we don't know the initial height at all. That's what we're trying to find. We're trying to figure out this initial height. But we do know that Aiden drops a pebble off a tall bridge. It takes the pebble 5.5 seconds to hit the ground below. So whenever it hits the ground, that pebble now has a height of 0. So I'm going to plug in a height of 0 here. And I know that it took 5.5 seconds for that to happen. So that is a time. So I'm going to plug in 5.5 here. Okay, and so if I do that, if I do 16 times 5.5 squared, I get 484. And I haven't given myself enough room here. Let me extend this out a little bit. Okay, so I've got 0 equals h sub 0, which is just a variable. That 0 doesn't do anything there. It's just telling us this is our initial height instead of regular height. Minus 484. And so I could add 484 to the other side. And so the initial height of this bridge is 484 feet. So if you could measure the amount of time that it takes for something to hit the ground, you can get a rough estimate of how tall that whatever structure you're dropping something from is. So this could be useful. I have heard people say, like, if you drop something, you need to count however many seconds and then multiply it by a number. That is not accurate because it's not linear. That pebble is not falling at a constant rate. But this would be accurate to whatever extent you can actually count it. Here is our next example. We have that the Empire State Building is 1,250 feet tall. How long will it take an object dropped from the top to hit the sidewalk below? So, again, we're going to think of our equation here. Our height, our original height is 12,050. So the Empire State Building is 1,250 feet tall, and then we are going to subtract the amount that the object falls due to gravity. It's always 16t squared, as long as you're on Earth and as long as you're measuring in feet and seconds. So in this case, we want to know how long it will take for the object to hit the sidewalk below. So the sidewalk below, the height when you hit the sidewalk is going to be 0. So we're going to put 0 for that height. And we've got 1250 minus 16t squared. And to solve this, we're going to subtract that 1250. So I'm going to get negative 1250 equals negative 16t squared. And then I can divide by negative 16. Let's go over here. Negative 1250 divided by negative 16 is going to give me 78.125. So 78. It's your phone. Let him see it for a minute. Okay, and then we just need a square root, both sides. He's watching videos. I'm trying to make a video. I'm trying to make a video. Alright, so we take the square root of 78.125. We get 8.8388. So if we dropped a pebble or penny or something, some object from the top of the Empire State Building, it would take almost 9 seconds for it to hit the ground. In fact, it might actually take 9 seconds because there's going to be some air resistance that we are ignoring whenever we do this. So this could be useful whenever you need to figure something out. Now, what we are going to start to consider is a situation where we are not just dropping something, but where we're throwing it up into the sky. So let's just consider for a second, imagine there is no gravity on Earth. If you throw a baseball straight up into the sky, what will happen to it? Well, if there's no gravity, that baseball is just going to go up and up and up and up and up and up forever, and it will not come back down. So let's consider this. If the baseball is thrown from a height of 5 feet, which is about shoulder height for some of us anyway, at 80 feet per second, record the height of the baseball below. Now, we are ignoring gravity. So the baseball would begin at 5 feet, and then every second it would travel 80 feet. So it would be at 85 feet. And then we would add another 80 to that, so we'd get 165 feet. And then we'd add another 80 to that, and so we'd get 245 square feet. And we'd add another 80 to that, and so we'd get 325 square feet. And then we'd get 405 square feet. Okay, so this baseball would just continue to go up and up and up an extra 80 feet every second if there were no gravity. Now, of course, we live in an environment where there is gravity, so we're going to have to consider that in a minute. But if we had no gravity, then the height of our baseball would do this. It would start off at 5 feet, and then it would go up an extra 80 feet every second. So I'm going to put 80 times t. So 80 times the amount of time that's traveled. And so that would give us these values that we see here in the table. Now, what we're going to be working towards, and we'll really get to this more next week than we will this week. So if we put gravity back in, we could, let's say for the baseball, the same situation. So we throw it from 5 feet, we throw it at 80 feet per second, And so that was our equation with no gravity. So if we want to add gravity back in and give us a picture of what the height of this baseball would look like on Earth, then we would add negative 16t squared here. Now, I'm going to type this in over here on Desmos real quick. H equals 5 plus 8t minus 16t squared. And let me, oh, sorry, that should be at 80. And let me click over here. Let's put that away. And I need to change my window a little bit so you can see it a little bit better. We need a higher maximum. Let's see. Let's go out just a little bit. All right. And you can see the shape of this graph. That baseball would go up, 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 up. It would stop right here. Looks like it goes maybe about 110 feet. Let's see. I think Desmos will tell us exactly. 105 feet. And then it'll come back down to the earth. And you can see this is really what happens whenever you throw something up into the air on Earth. So what we are going to look at this week is just a little bit of an introduction to this sort of stuff. So tomorrow there's going to be some videos for you to watch on Edpuzzle. The directions are on Canvas. It tells you how to get there. I think it should be pretty easy. I've already had a couple of my other classes do it. If you have trouble, let me know. Just some short videos on pumpkin chunking. And it's this competition they have in Delaware where they shoot pumpkins out of catapults. And then the rest of your assignment for the rest of the week is to create a catapult design. Now, you can either just actually make a catapult, or you can create a design for the catapult. If you create the design, I do want it to have a list of materials. I want it to look nice. I'll send you out some examples, but you will not get credit if your design for the catapult looks like this. I've had some that look about like this. This is what they try to turn into me. So that won't get you credit. It's got to be labeled. I'll show you some examples of what I'm looking at. I really would like for you guys to actually make a catapult and try to shoot it and send me a video of that. I'm going to be making one here at the house with my son and seeing if we can make one. I would love for you guys to do that as well. It's a little bit more fun if you actually build the catapult. However, I realize that we're all quarantined and we might not have the right resources and it might be a little hard to get those at this time. So if you don't have the stuff you need to make a catapult, you can just make a detailed design of what you would do. The design needs to be hand drawn. If you do a design, or you can draw it like on paint on the computer, but do not just look one up and send it to me that you can find on the internet. That is not what I want to see. Now, you can copy a design you found on the internet, but don't just send me a picture of the one that you found on the internet. It needs to be hand-drawn, or if you want to draw it on the computer like on paint or something like that, you could. So that is what you'll do. That is actually not due until Monday because we do not have online school on Friday. I was going to have it due Friday, but I forgot about the holiday. So that'll be due on Monday. Tuesday, you don't have anything you have to turn in, although if you go ahead and make your catapult or make your design, you could send that to me early. All right, so if you have any questions, please let me know. Again, I apologize for the meeting not going well, so I'll see if I can work on that, and I'll see you guys next Tuesday.